Yeah, good afternoon, students. Happy to see you all. Good afternoon. So, can you able to see me? So, and let me know in the chat box that my voice is audible to all of you. Yes. So, I am visible and audible, right? Okay. Thank you, Baba. Thank you so much. So, the same lesson, general organic chemistry, we are dealing with, and what was the last topic? What was the last topic we discussed yesterday? Can anyone tell me the topic that we have discussed yesterday? So majorly we have covered only one topic, and what is it? Yes, very good, Anjali. It is isomerism in organic compounds. And how many of you have studied the isomerism part yesterday? After completing the class, how many of you have read and studied the isomerism? So I should not ask such kind of questions, right? So I hope all of you have studied the isomerism part yesterday. Okay, so fine. Now going to the today's session. So today we are going to deal with the reagents in organic chemistry. Okay, so it is the reagents in organic chemistry. So it may be it is the kind of second part of this GOC lesson, and in the reagents in organic chemistry topic, today we are going to discuss about the electrophiles and nucleophiles, and breaking of bonds, and the reaction intermediate part. Okay, so these three topics are going to get covered in today's class. And moving on to electrophiles and nucleophiles, which is the first topic for today in reagents in organic chemistry. So let me discuss what is an electrophile first. Okay, what is an electrophile? So can any one of you tell me the definition or the meaning for electrophile? What is an electrophile? Just in a single line or single phrase, can you define what is electrophile? Can any one of you define what is electrophile? Any idea? The definition for electrophile, students? So have you heard of this word electrophile before? Which forms bonds? Okay, fine. But it is not the definition, no? Okay, which form bonds? Yes, obviously all the elements will form bond. That is good and correct only. But the more appropriate definition for electrophile be, okay, I'll let you know. So electro means electron. Okay, what is the charge of an electron? The charge of an electron is minus, negative, right? And phile means loving or liking, etc. Phile denotes the loving or liking. So electrophiles are the reagents which likes the negatively charged species. So who will like the negatively charged species? Only opposite charges attract each other, right? The one which is liking the negative charge would be an positive charged species, right? So electrophiles are basically the positively charged species. Electrophiles are nothing but the electron loving species or the electron liking species. Okay, and it is electron deficient in nature. It is electron deficient in nature. So we write the electrophiles like this only. We write like this. So basically they are positively charged species. Since they are electron deficient, they are positively charged species. Okay. And this electrophile is classified into two. One is charged electrophile and the other one is electron deficient electrophile. Okay. Charged electrophile, or I can say neutral electrophile. Electron deficient can be otherwise called as neutral electrophile. Okay. Charged electrophile and neutral electrophile. The examples of charged electrophiles you can see, as I have told you, the electrophiles are positively charged species. You can see some of the electrophiles being charged. R plus. What is R? R is an alkyl group. So who are alkyl groups? Methyl, ethyl, propyl. So all these are charged alkyl electrophiles, and Br plus, Cl plus, they are also an electrophile. NO2 plus, NO plus, all these are positively charged electrophiles. And the neutral electrophiles, which are also electron deficient in nature, are BH3, boron, aluminium. In here also you can see boron. Mostly the 13th group. The 13th group is made of boron, aluminium, gallium, indium, thallium, right? So mostly boron and aluminium containing compounds will be an example for neutral electrophiles. Got it? And here you can see RCHO. So what is this? This is an aldehyde. Okay, this is an aldehyde. So R is there, C double bond OH. So this is your electrophilic carbon. Okay, carbonyl carbon is electrophilic in nature, which is electron deficient in nature. And what is this? This is ketone. Okay, so who is the electrophile here? Again, the carbonyl carbon is acting as an electrophile. This is the electrophilic carbon. Okay, which is electron deficient in nature. So the other nucleophile will come and attack this particular carbon or this particular boron and aluminium electrophile. Okay, which are acting as a neutral electrophile basically. They are electron acceptors. They are always electron acceptors. Since they are electron deficient in nature, they are electron acceptor in nature. Okay, so this is about the electrophiles. So who are electrophiles, students? They are electron loving and electron deficient species. Okay, so now next I'll move to nucleophiles. So any doubt you have in electrophiles? If you're having any doubt, just put it in the chat box. Okay, is electrophile clear to all of you? Just put a thumbs up or just type yes in the chat box if electrophile topic is clear to you. Just the definition and the two types with their examples you're going to study under electrophiles. That's all. Okay. Is everyone clear with electrophiles? Shall I move on to nucleophile? Shall I move on to nucleophile? Yes. Okay. Thank you. So the nucleophiles are just the opposite of electrophiles. Electrophiles are electron-loving species. Nucleophiles are nucleus-loving species. So nucleus is basically made of a positively charged thing, right? So the one which is liking the positive charge will be made of negatively charged. So the nucleophiles are negatively charged species, and it is represented like this. Okay. And nucleophiles are electron-rich in nature. They are electron-rich in nature, just the opposite of electrophile. Okay. And the lone pair or pi-electron cloud will act as an nucleophilic center. The lone pair means the electrons which are not taking part in the bonding, right? So they are called as lone pair. So they are acting as a nucleophilic center. And in the double bond, triple bond, we have pi electrons, pi bonds, right? Those pi electrons or the pi bond will also act as the nucleophilic center. Okay. And nucleophiles are also classified into two. The one is charged nucleophile. The examples of charged nucleophiles are Cl minus, OH minus, you can see NH2 minus, HSO4 minus, etc. So basically there are three divisions under nucleophile. One is charged and the other one is lone pair. Lone pair containing nucleophiles are H2O. So in H2O, we have two lone pairs on oxygen. Okay, so they will act as a nucleophile. And in NH3, ammonia, nitrogen will have one lone pair. That will act as a nucleophile. And in case of ROH, ROH is nothing but the alcohol, right? So in alcohol, we are having oxygen, and each oxygen will have two lone pairs. So that will act as a nucleophile. And in case of RNH2, which is called as amine, in amine also, nitrogen is acting as a nucleophilic center. Okay. So these are the lone pair containing nucleophiles, which are not charged. Okay. And the pi-electron cloud containing nucleophiles are CH2 double bond CH2. What is this? This is an example for alkene, which is unsaturated. And what is this? CH triple bond CH. It is an alkyne. It is an alkyne. So in alkene and alkyne, we have pi bonds, right? So here only one pi bond and here two pi bonds we are having. So those pi electrons will act as a nucleophile. They will go and attack the electrophile. Okay? Clear for all? Electrophiles are electron deficient Nucleophiles are electron-rich species. Electrophiles are positively charged and nucleophiles are negatively charged species. And electrophiles are classified into two. One is charged and the other one is neutral. And nucleophiles are classified into three: charged, lone pairs, and pi electron. And examples under each category I have shown. Okay, clear for all? Shall we move on with the next topic? So I hope electrophiles and nucleophiles are clear to all of you. So now let's move on with the next topic, which is called as breaking of bonds. Okay, breaking of bonds. So we are going to break the bond in two different fashions. Okay, so the first breaking is called as, or the first cleavage is called as homolytic cleavage, and the second cleavage is called as heterolytic cleavage. Okay, what does mean by homo? Homo means same. Homo means same. And hetero means different, right? Hetero means different. So there are two different types of breaking of bonds. Breaking is otherwise called as cleavage. So there are two types. One is homolytic and the other one is heterolytic. Now let's discuss each and every type with the examples and with the mechanism. Okay. So first I'll move on with the homolytic cleavage of bonds or the homolytic breakage of bonds. So to understand this homolytic breakage, I'm going to take a molecule for you. Okay. What is this? It is A2 molecule. This is your A2 molecule. Okay. So here you can see both the atoms, both A atoms are bonded by a, cleavage means breakage. Bhavana, cleavage means, that's what I have told you, no? Cleavage means breakage of bonds. Cleavage means breakage. Okay, fine, good. So now, so these two A atoms are connected by a covalent bond. Okay, now each bond contains how many electrons? 2 electrons. Each bond contains 2 electrons. So since both the atoms are same, since both the atoms are made up of same atom, so the electronegativity of both the atoms will be same. Okay, what is electronegativity? The tendency of attracting or gaining the electrons towards itself. The tendency of attracting the shared pair of electrons towards itself is called as electronegativity, right? Now, since both the atoms are of same electronegative values, nobody is going to pull no one. Okay. So now what is going to happen? So these two electrons, they are going to break in a homolytic fashion. Means, so the first electron, this electron is going towards the first atom A and the second electron is moving towards the second atom E. Okay. So you should note the arrow which I have given here. It is like this, no? It is a single-headed arrow, which is otherwise called as fish hook arrow. You all might have seen the fish hook, right? The fish hook. So it should be like this. So this single-headed arrow denotes that only one electron is moving towards that particular atom. Okay. So the homolytic cleavage occurs. So electrons bond is in a homolytic fashion, means electron distribution is same. Electron distribution is same. And because of this particular homolytic cleavage, I am getting two species. I am getting two species, A dot and another A dot. That dot represents the electron. Okay. So an atom with single electron is called as radical. An atom with single electron on it is called as radicals. So basically, from homolytic cleavage, we are getting a radical. Okay, and this electron movement, as I have told you, it should be shown by a curved half-headed arrow, which is otherwise called as fish hook. Okay, and because of this, who is forming? Radicals are formed. Okay, now what is the condition? So which condition initiates this homolytic cleavage? Okay, which condition initiates this homolytic cleavage? So the first condition that is initiating this homolytic cleavage is the radiation, the ultraviolet radiation that we are getting from sunlight, UV radiation. Okay, that H nu. So if you find H nu If you find H nu above the arrow in any of your reaction, then you have to go for the homolytic cleavage of bonds. Okay. Not only this radiation, it is also initiated by peroxides. So I'll tell you some peroxides. The first peroxide is hydrogen peroxide, H2O2. And the second peroxide is C6H5, CO2 and O2. So this is another peroxide. So the first one is called as hydrogen peroxide. The second one is called as benzoyl peroxide. So if you find any peroxides above the arrow or below the arrow in your reaction, then you should know that the homolytic cleavage is happening in the reactant. Okay. And the third thing that is initiating this homolytic cleavage is giving the heat energy. Giving the heat energy. Heating up to 500 Kelvin. If you find any heating symbol like this, again, it goes for homolytic. So the light energy, heat energy, and peroxides. So these three leads to the homolytic cleavage of bonds. Okay. And from this homolytic cleavage, we are getting radical as the intermediates. Clear? So any doubt in the homolytic cleavage of bonds? Shall I move on with the heterolytic cleavage, students? Shall I move on with heterolytic cleavage? Yes? Yes? Yes or no? Okay. So the next is, yes. Thank you, Bhavna. So heterolytic cleavage. So for to understand this heterolytic cleavage, I am going to take AB molecule. Now both the atoms are not same, they are different. So let me take that atom B is more electronegative than atom A. So what this atom B will do? So 2 electrons are there in this bond, and atom B is more electronegative in nature. So the more electronegative atom will pull the electrons towards itself. So atom B is going to take atom A electron also. Okay. And atom A electron is also going towards B now. And from this, since atom A loses its electron, it is gaining positive charge, and atom B is taking that electron, and because of that, it is taking the negative charge. Okay. So now one more electron is added to this atom B. So from this, what we are getting? We are getting a positively charged species and a negatively charged species. Positively charged species are called as carbocation. Carbocation. If these atoms are carbon, then it is called as carbocation, and the negatively charged species are called as carbanion. Okay. So in homolytic cleavage, we got radical as the intermediate, and in case of heterolytic cleavage, we are getting carbocation and carbanion as the intermediate. Okay. Clear? Now, the electron movement is shown by the curved arrow. You can see there is a double-headed arrow here. Double-headed arrow. Okay, not in case of first thing. And because of this, positively charged cation and anions are formed. And the one which is initiating the heterolytic cleavage is a polar solvent. Polar solvent in the sense that can be water. Water is a polar solvent, or some other polar solvents like ether. Okay. So all the polar solvents are initiating the heterolytic cleavage. And not only this, intense heat. Intense means you are heating to a very high temperature. Very high temperature of heating also leads to the heterolytic cleavage. Okay. Clear? So basically, if you are taking a molecule with which is made up of same atom, it goes for homolytic. If you are taking a molecule with different atoms bonded with it, it goes for heterolytic cleavage. That's all. Okay. So now next I'll go for the intermediates which have been formed here from the cleavages. Okay. That is radical, carbocation and carbanion. So these three are called as reaction intermediates. These three are called as reaction intermediates. So who are the intermediate students? Radical, carbocation and carbanion. These three are the reaction intermediates. Okay. So in all the organic chemistry lesson reactions, you can see in the left hand side, there will be a substrate present in it. and the substrate is called as the reactant. Okay, so a reagent is now going to come and attack the substrate. Okay, now A is going to react with B, and AB reacts to give a transition state, and this transition state will then convert into an intermediate, and I have discussed about these intermediates, right? Those radicals and carbocation and carbanion. These are the intermediates. And intermediate again converts into a transition state again, and finally we are getting the product. This is the general mechanism of an organic reaction. Okay, let me show you a graph which represents these. So y-axis is taken as energy and x-axis is taken as reaction coordinate. So initially we are having a substrate and a reagent. So they react to give a transition state 1. This is transition state 1. And this again converts to an intermediate and is again converting to transition state 2. And finally transition state 2 is getting converted into the product, which is having very less energy compared to the reactant. Okay, got it? This is the graph. Now, the transition states which you can see here at very high energy levels, they are highly unstable. They are highly unstable. So you can see from the graph, the energy of the transition states are very, very high. We all know that energy is inversely proportional to stability, right? So since the energy is very high, the stability is very less. So that's why the transition states are highly unstable in nature. Okay, and you cannot isolate this transition state. Okay, isolation of this transition state is nothing but the compound. Okay, chemical compound only. So since it is unstable, you cannot isolate the transition state. It cannot be isolated. So these two are the points you have to keep in mind about the transition state. Now next I am going to deal with the intermediates. Okay. So the point that I am going to discuss under intermediates are just the opposite of transition state. Transition states are unstable and intermediates are more stable. Since the energy of the intermediate is very less compared to transition state, intermediates are highly stable and they can be isolated. They can be isolated. The intermediates are radicals, carbocations, and carbanions. So those three intermediates are isolated. Okay, clear? Now I'll discuss in detail about these three intermediates. Okay, going on with the first. So if you're having any doubt in between, you can raise your hand or put it in the chat box. Okay, don't hesitate to ask doubts. Now I'll go with the intermediates. So the first intermediate is free radical. Second intermediate is your carbocation. And the third intermediate is the carbanion. Okay. So moving on to free radical intermediate. Let's see some information about the free radical. So you can see. So CH3 dot. So CH3 with the single electron, which is called as methyl free radical, is shown to you as an example to understand the free radical. Okay. This is called as methyl free radical. And you can see as that unpaired electron, that single electron is located in the unhybridized p orbital. I told you, right? The shape of the p orbitals are dumbbell shape, and this particular p orbital is unhybridized. So in that unhybridized p orbital, the unpaired electron is located. Okay. So radicals are formed due to the homolytic cleavage of bond. Just before few minutes only we have discussed, and they are electrically neutral. They are electrically neutral. They are neither positive nor negative, right? So they are electrically neutral in nature. So this is the unpaired electron which is there on the unhybridized p orbital, and all the, just a second. So there is no power here in my place. So I just turn on my video once I get the power. Okay. Fine. So all the free radicals, all the intermediates are highly unstable in nature. So here free radicals are also unstable. Okay. Free radicals are also unstable. And Coming to the hybridization of this carbon, the hybridization of a free radical containing carbon is always sp2. sp2. There are 3 p orbital, only 3 is undergoing this hybridization, and the third p orbital, which is unhybridized, that only carries this unpaired electron. Okay, so that only carries this unpaired electron. So what is hybridization? It is intermixing of atomic orbitals, right? So this hybridization concept you might have studied in your chemical bonding lesson. So the hybridization of this particular carbon is sp2. So if the hybridization is sp2, then the geometry is trigonal planar, right? So that's why you can see the geometry as trigonal planar in the structure, in the screen. Just you see, this is a plane given to you and it is trigonal, like a triangle. No, it is trigonal planar in shape since it is sp2 hybridized. And you can see that there are only 7 electrons present around this carbon. So there is a carbon, and each carbon is bonded with the 3 hydrogen here, and 1 electron is in this unhybridized p orbital, right? So this bond contains 2 electron, and here it contains 2 electron, here also it contains 2 electron. So 2 plus 2 plus 2, 6. So 6 plus here 1, no, so 7. So we are having 7 electrons around this carbon free radical. Okay, so only if we have 8 electrons around an atom, it is attaining the octet configuration. And since we have only 7 electrons, which is less than 8, this particular species is electron deficient in nature. This particular species is electron deficient in nature. Okay. Yeah, since we have less than 8 electron, it is electron deficient in nature. And how many electrons it requires? It requires only 1 electron, right? To attain the octet configuration, it requires only 1 electron. So it just need only 1 electron. So it is not considered as a Lewis acid. Since it requires only 1 electron, which is very less, it is not considered as a Lewis acid. Okay, clear? So this is about the free radicals and its related informations. So the hybridization is very important, and the stability part is very important, and it comes from homolytic cleavage. These are very, very important. Okay. Shall I move on with the second reaction intermediate? Yes. Let's go with the second reaction intermediate. Second reaction intermediate, which is called as carbocation. Which is called as carbocation. So a carbon with a positive charge in it is called as carbocation. So you can see the carbocation here, carbon with positive charge. Okay. And you can see the empty p orbital. Here you see the unhybridized p orbital is empty in case of carbocation because it has left, it has given that electron to the other species. Okay. So this carbocation is obtained from the heterolytic cleavage of bond. Right. So both carbocation as well as carbanion. So both are obtained from the heterolytic cleavage of bonds only. Okay. And they are positively charged in nature. And you can see the empty p orbital here on the screen. So it is unstable. All the intermediates are highly unstable. And coming to the hybridization of the carbocation, it is also sp2. Hybridization of this carbocation is also sp2. And since only 6 electrons are present around each carbon, you can see there are only 6 electrons, right? It is not 8. It is just 6. So it doesn't attain the octet. So it is electron deficient in nature. It is electron deficient in nature. So since it requires 2 electrons to complete the octet, it is very highly electron deficient in nature. And so it acts as a Lewis acid. It is acting as a Lewis acid as well as electrophile. They are acting as a Lewis acid as well as an electrophile. Lewis acids are nothing but the electron deficient species. And electrophiles are also nothing but the electron deficient species. Got it? Carbocations are Lewis acid as well as electrophile. So these are the points under carbocation. Okay, it is formed by the heterolytic cleavage. This you have to make a note of it, and the hybridization, and it is an electrophile as well as Lewis acid. These are the very important points that you have to take a note of. Okay. Then coming to the third reaction intermediate, which is called as carbanion. Third reaction intermediate is called as carbanion. So what is a carbanion, students? What is a carbanion? What is a carbanion? So a carbon with negative charge. A carbon carrying negative charge is called as carbanion, right? So you can see the carbon bearing the negative charge is a carbanion. And carbanion is also formed from the heterolytic cleavage of bond. Is also formed from the heterolytic cleavage of bond. And what is the charge of carbanion? It is negatively charged. Carbanions are anion means it is negative, right? So anions are obviously negatively charged in nature, and you can see the two lone pairs present on the hybridized orbital. So now this orbital is not an empty or normal p orbital. It is the hybridized orbital. I will tell you the hybridization in the next point, okay? And this carbanion is also unstable in nature, highly unstable. Now, coming to the hybridization, it is sp3. Carbanion is sp3 hybridized. So we have 3p orbitals. Okay, we have 3p orbitals, and all the 3p orbitals are mixed together. So 1s, 2s, and 3 2p. They will mix with each other to form the sp3 hybridized orbital. Okay, so 4 sp3 hybridized orbital will form. Okay, among the 4 sp3 hybridized orbital, so one is used for the formation of bond with the hydrogen, and the second is for second dihydrogen. Third orbital is for third hydrogen. The fourth sp3 hybridized orbital is used for the lone pair. Okay, that is only you are seeing here. So this is the shape of the hybridized orbital. That's why it is looking like this. Only this lobe is shown to you and lone pair is present on it. So the hybridization of the carbanion is sp3, and you can see negative charge in it, right? So it is electron rich in nature. It is electron rich in nature. All electron rich species will act as a Lewis base as well as a nucleophile. So electron rich species are called as Lewis bases, and they are nucleophiles. Got it? So this is about the carbanion. So any doubt in the reaction intermediates which I have discussed with you today? Radicals, carbocation and carbanion. So all of you are clear and thorough with it, right? No doubt, right? If you're having any doubt, put it in the chat box, okay? Now I'll go to the stability of these intermediates. Stability of intermediates. So first let me start with the free radical. I'll start with the free radical. Okay. Free radical. Difference between Lewis base and the nucleophiles. So mostly Lewis bases are the negatively charged species, but in case of nucleophiles, if negatively charged species will also act as nucleophile, whereas neutral nucleophiles are also there, which I have discussed with you. Right? They are also nucleophiles. They are also nucleophiles. And coming to the free radical, I have discussed CH3 dot, right? CH3 dot. This is the methyl free radical. And if I replace one of the hydrogen with R group, alkyl group, I'll get RCH2 dot. This is called as primary free radical. And if I replace 2 hydrogen by 2 R group, what I will get? I will get R2CH dot. This is called as secondary radical. If I replace all the 3 hydrogen by 3 R group, I will get R3C dot, which is called as tertiary radical. Which is called as tertiary radical. Okay. Now, among these 4 systems, the tertiary free radicals are more stable. Tertiary free radicals are more stable. So the order of stability is this. Got it? So the same order you have to follow for carbocation also. Same order is followed for carbocation. So CH3 plus is methyl carbocation and RCH2 plus is primary carbocation and R2CH plus is secondary carbocation and R3C plus is tertiary carbocation. Again, the tertiary carbocation is more stable. Okay. Now coming to the stability of carbanion, it is just the opposite of these two. So which carbanion is more stable, students? This is methyl carbanion and this is your primary carbanion. This is your secondary carbanion and tertiary carbanion is R3C mix. Okay. Now, methyl carbanion is more stable, then comes primary, then comes secondary, then comes tertiary. Okay. I'll give you the reason for the stability, like why tertiary carbocation and carbon-free radicals are more stable. So what is the reason for that? That will be discussed in the next topic. Okay, which is called as electronic effects. Electronic effects. Got it? So now you note down the stability of intermediates. Now you note down the stability of intermediates. Take a screenshot of it and note down the stability. It is very important. It is very, very important. So shall I go on with the next topic? Shall I go on with the next topic? Students, shall I go on with the next topic? Yes. Okay. So the next topic is electronic displacement effects. So basically, there are totally 3 to 4 effects we are having. Okay. And in today's class, I'll try to complete as much as possible. The first electronic effect is inductive effect. Second is hyperconjugation. Third is resonance or mesomeric effect. And the last one is aromaticity that will also be included here in this electronic displacement effects. Okay. So coming to the first effect, which is called as inductive effect. So to understand this inductive effect, let me take a molecule. So it is of formula AZ. And each bond contains 2 electrons and these are the 2 electrons which you can see on the screen. Okay. Now, since let me take that atom Z is more electronegative than atom A. So what this Z atom will do? It will take the electron of atom A also towards itself, right? So both the electrons are now moved towards atom Z because it is electronegative in nature. And because of this pulling of electrons towards one direction, the bond is getting polarized. The bond is getting polarized. So you can see in one side there is partially positive charge and in the other side you can see there is a partial negative charge. So this small delta denotes the partial negative and positive charge separation. Since Z atom has gained the electron, it is taking negative charge and A is donating the electron, so it is getting positive charge. Now the bond is polarized. Okay, so the polarity caused in the sigma bond is called as inductive effect. Okay, this bond is called as sigma bond because it is formed by the head-on overlapping of the orbitals, and we have only one bond, that is sigma bond. So now that sigma bond is polarized. Okay, so the polarity caused in sigma bond is called as inductive effect. So this effect arises due to the electronegative difference between the atoms. Yes, right? So since the electronegativity difference is very large between A and Z, I already told you atom Z is more electronegative than atom A. So because of this electronegativity difference, the bond is getting polarized. Okay. So let me show you with the more appropriate structure. You can see here So now this is atom Z, which is more electronegative in nature. It is pulling the electrons towards itself. It is pulling the electrons towards itself. So it is gaining partially negative charge, and the adjacent carbons are getting positive charges. And you can see it is only one partially positive. Here partial positive. Here 3 plus and here 4 plus you are having. So what is the meaning? What is the concept that we are getting? It is a permanent effect. You cannot change it, and it is very weak. It is significant only till third carbon or fourth carbon. Suppose if a compound contains more than 5 carbon, or if it contains more than 10 carbon, this defect is significant only till third carbon or fourth carbon. Okay, so it is a distance dependent effect. Okay, if you move very farther away from this electronegative atom, this effect, it will get reduced. Inductive effect will get reduced. So it is a distance dependent effect. So it is inversely proportional to this. So when the distance is more, inductive effect is very less. So that's what you can see here. When the distance is more, the inductive, the polarization is very, very less. Okay, here 4 plus we are having, and here only 3 plus. Okay, so the effect becomes very less. Clear? So this is about the inductive effect. The definition is very important. It is due to the electronegativity difference is very important, and it is a distance dependent effect. 3 points are very, very important. Okay. Now coming to the next point, there are 2 types of inductive effect. One is called as positive inductive effect, and the other one is called as negative inductive effect. So what is positive inductive effect? In this case, the electrons are shifted towards the carbon chain. So you can see here, electrons are shifted. So the electrons which are here, they are shifted towards the carbon chain. Carbon is pulling the electron towards itself. Okay, means the particular group which is present here, it is called as positive inductive effect. It is donating the electron to the carbon. Okay, so who are those groups? Who are those plus I groups? The plus I groups or the electron donating groups are these. These are the electron donating groups or plus I groups. The carbanion, NH minus, O minus, all these are electron donating groups. Got it? And coming to the second effect, which is minus I effect. In minus I effect, all the electrons are shifted away from the carbon chain. They are shifted away from the carbon chain. So all the electrons you can see, they are going away from the carbon chain and they are going towards this Z. So Z is getting negative and carbon is getting positive. So what is happening here? So now this group is an electron withdrawing group. That's why it is called as minus I group. Now this group is your electron withdrawing groups, and the examples for electron withdrawing groups are the order which you can see on the screen. So these many electron withdrawing groups we are having. Mostly all the electrophiles, electron deficient species, and more electronegative atom containing species, they will fall under this category. Okay? Clear? Now this particular order, this particular electron donating withdrawing order which you can see on the screen, they are determined in the experiment. Okay, the order of inductive effect is determined experimentally. So that's why even though oxygen is more electronegative than sulfur, sulfur is pulling or it is withdrawing the electrons more effectively compared to oxygen. Right? So in the order, SH is having the more electron pulling capacity, electron withdrawing capacity compared to OH, right? The one which is having more electronegativity only will pull more effectively. Oxygen is more electronegative. So obviously OH should come first and SH has to go next. But in the order you see SH is coming first and OH is coming next. So it is determined experimentally. Experiment shows that SH is having the more electron withdrawing power than OH. That may be due to some other various reasons. Okay, clear? That we will discuss in the later part. So this is about the first effect, which is called as inductive effect. So any of you have any doubt here in inductive effect? If you're having any doubt here in inductive effect, just raise your hand. If it is clear to you, Just put yes or give a thumbs up. Shall I go on with the next effect, students? Are you all listening? Yes. Thank you so much, Anjana. So the next effect is hyperconjugation. Yeah. Next effect is called as hyperconjugation. Now, what is hyperconjugation? The sigma bond overlaps with the p orbital. The sigma bond orbital overlaps with the p orbital. Basically, hyperconjugation means helping. The one which is very electron deficient in nature, for that particular electron deficient center, the one which is adjacent to it will go and give its electron to that center and make it more electron rich. So it is basically the helping tendency of the adjacent bonds. That is called as hyperconjugation, which arises due to the overlapping of sigma bond orbital with p orbital. So who is that sigma bond orbital? Basically, the sp3 hybridized sigma bond orbital overlap with the p orbital. Okay, and more the number of alpha hydrogens you are having in your substructure, more the number of alpha hydrogen, more the hyperconjugative structure, so more will be the hyperconjugation effect. Now, what is meant by alpha hydrogen? What is meant by alpha hydrogen? So before going on to the explanation of that, I'll show you the fourth point. The effect is observed in carbocation. The effect is observed in carbocation. So I'll take a carbocation for you. So this is the carbocation, and it is what I can say. I'll take CH3, CH2 plus. This is your ethyl carbocation. CH3, CH2 plus. Now this center is electron deficient in nature as it is a carbocation. Now the carbon which is adjacent to this carbocation is called as alpha carbon. Okay. And the hydrogens which are attached to that alpha carbon, they are called as alpha hydrogens. So now these are the alpha hydrogens, and in this case we are having 3 alpha hydrogens. If there are 3 alpha hydrogens in the structure, there will be 3 hyperconjugative structure for you. Okay, so now how these alpha hydrogens are going to help this carbocation? So they'll help in this manner only. Carbocations are sp2 hybridized. Carbocations are sp2 hybridized, and this particular carbon is sp3 hybridized. Just a second. Yeah. So now this particular carbon, it is sp3 hybridized, and it has 4 sigma bond, and the hybridization of carbocation is sp2. Just before a few minutes only we have discussed the hybridization of the carbocation, right? Now the alpha hydrogen, which has 2 electrons in this particular CH bond, is now going to give its 2 electrons to the CC bond. Now because of that, we are going to get a double bond here. Now the positively charged carbocation is now neutral in nature. Now this hydrogen has donated its electron to that carbon, and it leaves out as H plus. It leaves out as H plus. Okay, basically hydrogen is helping the carbon. That's all. Hydrogen is helping the carbon. So since we have only 1 alpha hydrogen here, only 1 hyperconjugative structure is possible. If all these are hydrogens, then we would get 3 hyperconjugative structures by the donation of these electrons. Okay. So more the number of alpha hydrogen, more hyperconjugative structures are possible. So more stable is that molecule. So that's why you can see the stability of carbocation is directly proportional to the number of hyperconjugative structure. So this is what I have explained you. Now you can answer this question, right? So write the following species in increasing order of their stability. So this is R3C plus, which is called as tertiary carbocation, and this is R2CH plus, which is secondary carbocation. This is RCH2 plus, which is primary, and this is called as methyl carbocation. Okay, I told you that tertiary carbocations are more stable. Tertiary carbocations are more stable in nature, right? So here in the first case, there is no alpha hydrogen, whereas in primary you can see there are 3 alpha hydrogens, and in case of secondary you can see how many alpha hydrogens are there in case of secondary carbocation, students? So 3 plus 3. So these two are the alpha carbon, which is adjacent to this carbocation. So to that alpha carbon, 6 hydrogens are attached. So 6 alpha hydrogens are possible for secondary carbocation, and 9 alpha hydrogens are there for tertiary carbocation. Okay? So that's why tertiary carbocation is more stable since it has more number of alpha hydrogen. Got it? Because of more number of alpha hydrogen, more number of hyperconjugative structures are possible, and the stability is like this. Tertiary is more stable. Clear? So now I hope you get to know the reason for the stability of the tertiary carbocation. Okay? So any doubt from the hyperconjugation? So just remember this point. This point is very important. Number of hyperconjugative structure is directly proportional to the stability. So this can be found out from the number of alpha hydrogens attached to it. Okay, this is very, very important. So this is enough for today. So today we have discussed all the reagents in organic chemistry, that is electrophile and nucleophile. Okay, electrophiles and nucleophiles I have discussed with you. And secondly, I have discussed the homolytic and heterolytic bond cleavage with you. And thirdly, we have discussed the electronic effects, right? So there are 4 effects, and the first effect was inductive effect, and the second effect is hyperconjugation. So these 2 effects I have discussed today. So the next effect, the resonance effect, I'll discuss tomorrow. Okay, just go through these topics which we have seen today and come for the next class. Okay. Okay, students, thank you so much. Bye-bye. Thank you for listening to the class. Yeah, thank you.